Okay. Hello, everyone. Thanks again. Thank you to the organizers for inviting me to this wonderful conference on big data, on complex systems. So I must admit that I'm fairly new to this data science game. So my training is numerical partial differential equations, and in particular solvers, fast solvers for such systems. So my talk today is going to be on parallel and time algorithms for data assimilation problems. This is joint work with Martin Gander at the University of Geneva, Julien Salomon in INRIA in Paris, and his PhD students who is in his last year of his PhD at Sébastien Reyes-Rifo from Paris Dauphine. So what do I have in mind? What sort of problem I'm thinking about? So I'm thinking about a physical system where the dynamics are well established, and there's a governing PDE, and the difficulty here is that I have some unknown or uncertain parameters, and I would like to adjust my model based on observed data to try to get a good approximation of the actual trajectory. Okay, so if you think of weather forecasting, we do know how the atmosphere interacts with the ocean and all that. So we have good physical models for that. What we don't actually have is data on the initial conditions, because we don't know what the state of our system is precisely. However, we have some measurements. So for example, there are these y's that are measurements, at certain locations. So basically, we would like to adjust our forecast based on some approximation of the initial conditions, for example, which would have given us, for example, this dotted line. Okay, and then based on the which one is which? Okay, so this is the one where based on our best understanding of the initial data, we would have gotten this. But given that we now have more observations, we'd like to adjust our initial conditions and our data in order to get a corrected forecast. Okay, so that's the kind of thing that I'm thinking about in the back of my mind. So one of the examples I'm going to present is, for example, contaminant tracking. So you have a body of water, a lake or something, and then there is some sort of pollutant, some contaminant that's seeping into the water, for example. Okay, and we assume that we know how the water flows in the body of water. For simplicity, I use the advection diffusion equation where the flow function is known in a sense. So I'm trying to track the concentration, which is denoted by y here, and there's a source term, which is where the contaminant's coming from. Okay, so the first variant is that I don't know how much of the contaminant is being released, although I know what the location is. So here is my governing equation, and then based on some data, some observed data that that I have over a certain period of time, 0 to capital T, I would like to find the forcing function which minimizes the discrepancy between what I observe and what I predict. Okay, so that's one variant. So here is a small video. So suppose that we have some contaminant that's coming in from the middle of this body of water here, and then I have observations, so sort of on the boundary, well, in the region close to the boundary, and I observe that initially there's no contamination, and then at some point I see that there's some sort of I detect some contamination, and then it falls back to 0, and I'd like to know based on that what's the best guess of what the concentrations are in the whole body of water. Okay, so let me play that. So, and this is all calculated, based on. So you see, as time evolves, okay, so this is going to loop. Oh, it's not going to loop. So initially there's nothing, and as soon as I detect some contamination, I see that I can deduce that there's some contaminants released in the middle, and it has to be a little bit before because it takes time to flow from the middle to this boundary, and then as there's no more observation, I see that the thing dissipates and so on and so forth. So this is the kind of thing that I'm thinking of. So that's one variant of it. A second variant would be I know the forcing function, but then I don't know the initial conditions. So it would be a very similar looking mathematical formulation where now I have initial conditions that is unknown, and then I'm trying to choose based on my observations, again, to minimize the distance between the observed data and the predicted data. And I choose the V that minimizes the discrepancy between the observed data and the predicted one. Here there's a regularization term, so I assume that I have some sort of idea of, some initial approximation of what the initial conditions would be, but of course that's not the right one. It doesn't match the data, so I'm trying to choose the one that makes it better. Okay. Now there's a third variant, which is, before I said, I try to minimize the discrepancy, given data from 0 to capital T. Now what happens if I have an infinite stream of data that keeps coming? Is it possible to have a method that sort of converges to the actual observed trajectory as capital T goes to infinity? So that's a third variant. So I'm going to talk about, and then of course, I talk about weather forecasting and contaminant tracking. There are also other applications. So in aeronautics, you can have aircraft design in order to reduce noise. So that's some sort of optimization problem given, a model, a physical model. Oil and gas, they call it history matching. If we know the production data from previous instances, then we can sort of try to figure out what the content of the underground formation is in terms of oil and gas, what its current state is, and then we adjust the, our prediction based on, this available data, okay? So what are the challenges? So first of all, huge system size. We were talking about the PDE here. So if you want high resolution, you want to have a very fine discretization, you want to have many time steps as well. So right off the bat, you get really large systems. Stiff nonlinear problems, you're integrating a PDE, so you expect some sort of stiffness. You sometimes will also have real-time requirements because so if you're predicting the weather, for tomorrow, if your calculation takes more than 24 hours to run, then you're not predicting anything. So there are hard constraints on how fast these things are supposed to run. So I actually looked up what the fastest computers are as of this November. So it's very curious. So something has changed now. I think back in May 2018, that on the top 500 list of the most powerful computers, Taihu Light in China was still the fastest in terms of the number of flops. But this latest one that was released in November, turns out we have a new winner, which is the Summit supercomputer from Oak Ridge National Lab. So 1 and 2 is now in the US, and 3 and the old 1 and 2 became the 3 and 4. So there's still this sort of improvements in our computing power. But of course, now these supercomputers, they are not one computer with that is very fast, but they are really a collection of cores. So here we're talking about in the order of millions of cores. Okay, so what we have to do if we want to exploit this computing power is to take our problem and then divide it into pieces that can be run in parallel and feed it into the different cores in order to get to have everything running at the same time. Instead, so if you have a sequential algorithm, it's not going to make this thing is not going to run any faster, because if you're only using one core, then there's only so much you can do. So parallel computing is really the game here. So the rest of the talk is going to be divided into 2 parts. So the first one is going to be assimilation over finite time. So that's when my data is living on a time interval 0 to t. And then the second part will be on what happens when I have a data stream that can go on forever. Okay, the techniques are a little bit different. So if you have the finite time assimilation, so this is the problem I'm thinking about. Okay, you can write down the first order optimality conditions. And that's going to give you an adjoint system where lambda is the Lagrange multiplier, so to speak. It's the adjoint variable. And this equation will be satisfied at the same time as the original state equation. And here there's a link between the forcing function and the adjoint variable. Here it's proportional because I'm doing distributed control. So immediately what you notice is that this adjoint variable is also a differential equation, but it evolves backward in time. So it has some final condition at capital T, and then it evolves backwards. Okay, and it's tightly coupled. There's in the equation for lambda, there is the y term, and then in the y equation, there's a lambda term. Okay, so it's not a pure initial value problem. You can't just time step through it. Okay, so how do we solve this sort of system? And it's huge as well. So now you have time discretization. You have many time steps, and each time step has many unknowns. That is, that keeps track of the state, which comes from a discretization. So you have many, many unknowns. Okay, so if you want to solve this, in an architecture where you have many processors that can run in parallel, one possibility is to use what is called domain decomposition. So what you do is you take your time interval, 0 to capital T, and then you chop it up into smaller time intervals so that you have smaller problems, smaller data assimilation problems, on each of these subintervals. Okay, so now each of these, if you know the initial condition for the state and the final condition for the adjoint, then this is a completely well-defined problem that you can solve independently from one another. Okay, so now you have many smaller problems which you can solve in parallel. Now, of course, you can't solve this one and expect to have the global solution because you're going to have some discontinuity of the trajectory across these cuts on the time interval. So you're going to have to iterate, and at the end, you're going to hopefully you'll converge to a solution where the continuity conditions are satisfied. So if the blue connects with the blue across subintervals, then you have the exact solution. Okay. So basically, it's an iterative method in order to drive these discontinuities to 0. Okay, so you can think of domain decompositions that way. So this will be domain decomposition in time. You can also do domain decomposition in space, but that's an entirely different talk altogether. Okay, so this idea has been around for a while. So for the wave equation, there's a paper by Laniese and Leugering in 2003, and this is very closely related to the optimal control community because it's essentially, trying to figure out the best forcing term to match a trajectory is almost the same as saying, trying to find a control that steers your state, along a particular trajectory. So this is very closely related. So there's a lot of work done in the optimal control community. For parabolic problems, there's a preconditioning method by Heinkenschloss in 2005, and then more recently, there's a time domain decomposition which is related to this work. Okay, so our contribution here is basically to use something that is very similar to an optimized Schwartz method, so a block Jacobi but with some overlap in the time direction. Okay, so what we do is we take our assimilation domain, time domain, we cut it up into small overlapping intervals, and then we basically iterate, and then now these different intervals have to communicate amongst each other using the initial and final conditions, okay? So then what you do is, well, first of all, if you ignore the red, you can say, okay, at every iteration, I can say, this first subdomain as a final condition, I would like to have the same lambda value as the subdomain to my right, okay? So that, if my iteration converges at the fixed point, then I have continuity of the adjoint variable across subdomains, okay? And I do the same thing for the state variable. So for example, the second subdomain should have initial conditions that is consistent with the same location in the first subdomain, okay? So if you ignore the red bits, and you just look at the y equals the y and the lambda equals the lambda, that is what is called, Dirichlet transmission conditions, because you're just matching variables. It turns out that, you can prove something about the convergence of this method. I'm going to show you in a minute. But it doesn't give you the best convergence rate, okay, because there are no knobs to turn. I mean, basically, it is what it is. It's going to do whatever it does, okay. Another idea is what is called an optimized Schwartz method, where you will take linear your initial and final conditions are really linear combinations of the state and the adjoint, and there's a proportionality constant Q and P that you can tune. Okay, so now you have more knobs that you can turn, and then you can try to choose these parameters properly, and if you do that, then you get much faster convergence. So that's what I'm going to show you. Okay, just a word on what does changing these boundary conditions make the problem more difficult to solve? And the answer is not really, and it's because it also corresponds to a slightly modified minimization problem where you basically have some sort of target state at the end and some sort of uncertainty in the initial condition. So it's already of the same form as what you would have started with. So it doesn't make the problem and the subproblems any more difficult. Okay. So now the main question is, when do we have convergence for what values of P and Q, and how do I choose these P and Q to optimize for convergence? So here is the first theorem that I'm going to state. So this is when P equals Q equals 0, meaning that I'm just matching Y's and matching lambdas. I'm not taking linear combinations. Then under some assumptions, you can prove that the method actually converges, and then with a contraction factor that looks like this. Okay, so a couple of things to notice here. So what does the convergence depend on? So first of all, it depends on the overlap. So the more overlap there is between my two time subintervals, the faster the convergence, which is reasonable because you're doing a little bit of duplicate work, so you'd hope that it pays off. Okay. A second thing you can notice is that this contraction factor only depends on the minimum, the smallest eigenvalue of A, which is the operator sitting on the right-hand side. So the equation is y dot equals. So it's if you have y dot equals minus A of y, then it depends on the smallest eigenvalue, but not the largest one. So that's a nice feature for this method because, as you may probably know, if you discretize a partial differential operator, the finer your grid is, the larger the largest eigenvalues are, and that goes to infinity. So you don't want something that depends on the largest eigenvalue. That would mean that your method is not scalable. As you refine the grid, your behavior changes. But if it depends on only the smallest eigenvalue, usually that's the one that is fixed. Okay, as you refine the grid, the smallest eigenvalue is more or less constant. So that shows you that this method has the potential of being mesh independent. So here are two examples. So what am I plotting here? The y-axis is the contraction factor. Okay, so anything above 1 means divergence. Okay, so above 1 is bad. Below 1 is convergent. And you want it to be as small as possible. Okay, and on the x-axis, I'm plotting the eigenvalues of A. So if A has eigenvalues between, say, 10 to the minus 1 and 10 to the plus 2, then the relevant range that you should look at for the contraction factor is from here to here. Okay? So here are a couple of examples. The first one is precisely how what it was stated in the theorem. And the second one is for a slightly modified problem where I have uncertainty in the initial data. Okay? So you can see that if there's no uncertainty in the initial data and I'm just trying to figure out the forcing function, then using Dirichlet transmission condition works. Okay? If you just match state and adjoint, then you eventually get some convergence. But if you have very small eigenvalues, so for example, if you have a Neumann boundary condition everywhere for a heat equation, then you get very small eigenvalues and then your contraction rate factor is rather close to 1. So it's going to take you a while to converge. And then if you have uncertainty in the initial conditions, then it's way worse, and you actually can get divergence. Okay? Now, if you have a couple of knobs to turn, so this is with an appropriate choice of P and Q, then for both cases, I can choose the right P and Q so that the new contraction curves, the contraction factors are down here and down here. So you see that now I can choose it in such a way that everything fits between 0 and 1. So I have convergence of the method as long as A has only positive eigenvalues, which is, for example, for all diffusion problems you'll have that. And then I can also improve, even when it was converging before, I can improve on the rate of convergence. Okay? Just a couple of numerical examples. This is a simple heat equation with a Crank-Nicolson discretization, Dirichlet or Neumann boundary conditions in space. So the Dirichlet means that your smallest eigenvalue is not close to 0. It's somewhere around 10, actually, for the unit interval. Whereas Neumann means that you have a 0 eigenvalue. And then you see that, so actually there are 6 curves here. That each of them is a pair of curves, so I refine the grid once in order to show you that it doesn't change the contraction at all, meaning that I do have some sort of grid mesh independence. And then here, the Dirichlet, if you run 10 iterations, you're essentially at round-off error, and that's because the Dirichlet, it has its smallest eigenvalue is far away from 0, so everything works well. But as soon as you have a Neumann condition, then everything converges very slowly. You see here, if you just use matching states and matching adjoints, so that's not going to work very well. But if you tune your parameters correctly, it's going to go down much more quickly. So as a second example, I go back to that contaminant problem with one observation point here, as a function of time, and then you see that for 2 intervals, 4 intervals, 8 intervals, 16 intervals, everything converges. So this is a stationary iteration, and this is with GMRes with Krylov acceleration. You see that everything sort of converges in a reasonable number of iterations, for different numbers of time intervals. How much time do I have? 6 minutes? Okay, thank you. Yeah, that should be enough. So that's assimilation over finite time. Now, what happens if you have your data that continues, with for all t? Then you don't get the adjoint equations anymore. You can't use adjoint techniques because you don't have a final condition for the adjoint. Okay, so it doesn't work. So there's a different technique of doing it. Okay, and that is what is called a Loonburger Observer. Okay, so let me introduce some notation here. This is the original ODE system. Once you discretize, your PDEs, you get a large ODE system. This is the thing that you actually want to approximate, but that is mostly unknown. Okay, even the dynamics may be a little bit off. Okay, but it's a good. So y tilde is the trajectory which I can actually calculate, and which I hope will converge to the exact trajectory as time goes on. Okay, so how do I define y tilde? So I take the dynamics for my original problem, and I add to it a matrix L multiplied by this difference, where I have a difference between the observed data, that's my yd, minus the calculated trajectory multiplied by an observation matrix, so that it's consistent with what I'm observing. Okay, so this is in some sense the error term, the difference between the observed data and the predicted data, and I multiply that by a matrix L, and then I put that into the equation as an extra term. Okay, so if you take this and the previous thing, and also I don't have exact initial value, so that's the thing that I'm trying to overcome by using data that I observe. Okay, so if you subtract this equation from this equation, you'll see that the error satisfies an ODE which you can solve, and then you see that the difference between the exact and approximate trajectory will behave like an exponential in time times the difference in the initial conditions. Okay, so it now all hinges on what this matrix looks like, A minus L times C. Now there's a classical theorem from, again, control theory, that says that under some assumptions of what your A and your C is, and that's complete observability. In the finite dimensional case, you can set up a large matrix and look at what the rank is. In theory, that will tell you whether your system is completely observable. If your system is completely observable, then you can choose the matrix C so that you have you can place the eigenvalues anywhere you want. Okay, it's a pole placement problem in the control theory parlance. So what you can do is you can choose your L so that A minus LC only has eigenvalues on the open left half plane. And what that would do is your exponential in time is going to go to 0 as t goes to infinity, which is what we want. That tells you that if you assimilate for long enough, then your calculated trajectory is going to converge to your exact one. And so that's your goal. And there are standard algorithms to design this L. Here's a few of them. Okay, but now here are some questions. How long do I need to assimilate the data in order for the difference of the error to be smaller than a given tolerance? Okay, so that's not known a priori. Okay, and also how long do you have to? How do you actually introduce parallelism in this? Because now I only have a pure initial value problem. Okay, right. So then it's like saying, can I calculate the weather for tomorrow if I don't know what the weather is today? I mean, that sounds hard, right? So as it turns out, there is a way of doing this, and it's one way. There are many ways. In fact, there's a survey paper on this. But one way is called the parareal algorithm, which is introduced in 2001 by Lyons, Madé, and Turinici, a group in France. And basically, the trick is it uses two integrators, one that is fine, accurate, but expensive, and another one that's coarse, but inexpensive, but very fast. And then you basically chop up your integration interval into several subintervals. You assume some initial conditions for each of the subinterval. You integrate using your fine integrator. And then you try to correct these initial conditions using the cheap one. Okay, and you can interpret this as some sort of approximate Newton method for solving for the initial conditions. I'm going to skip this example. The only thing to notice is that if you have 32 intervals, you can get the convergence with to something that's under 10 to the minus 10 in like 6 or 7. So that's how you get the speed up. Okay, if you don't need to iterate that many times and you still get a good enough answer, then that's how you get the speed up from, because you assume that the coarse integrator is cheap. Okay? So now we know how to do the assimilation in parallel if the time window is fixed. But now the time window is not fixed. So what do we do? So here is an algorithm, okay, that that is new, that we propose. So you assume some initial assimilation length. You don't know whether that's long enough. Okay? So you just do it, and then at the end of that interval, you try to estimate the assimilation error, okay? And if the error is small enough, then you say, okay, that time interval is good enough. If it's not good enough, if the error is still too large, then you assimilate on the next piece of the time interval and so on and so forth. So in each of these windows, you can run your parareal algorithm, you can get some sort of parallel speed up, and then if it's not good enough, then you keep doing that until it's good enough. So now the question is, how many parareal iterations do I need to get a good enough solution? Well, if you fix the number of iterations, then initially it's okay because the assimilation, you're still far away from the exact trajectory. So the error is going to be dominated by the assimilation error. But if you keep doing the same thing, at some point it's going to plateau out. And that's because now your solver error, your parareal error is going to dominate. So there is so what we need to do is to dynamically choose the tolerance so that it matches the assimilation error at the time. Okay, so what that means is you need to choose larger and larger k, larger and larger number of iterations as you move along in order to control the solver error so that it matches the assimilation error. Fortunately, the k doesn't grow very quickly because every extra iteration you take, you'll lose on parallel speedup. So fortunately, it doesn't grow that quickly. So here's a very simple numerical example. This is very much work in progress, a little 2 by 2. And then here is the error, and the different colors show you how many parareal iterations you need to take in order to have an error that at least matches, you know, the assimilation error. So initially, you don't need to take many iterations at all because, you know, you're so far away from the trajectory anyway. And then you see that as you go along, you need to take more and more. So here it will be 7 iterations. But the patch where 7 iterations is enough versus the patch where 8 iterations is enough, you know, it grows. So you don't actually need to take that many of them. So I'm out of time. Thank you for your attention.